Now let's consider the behavior of our last two operators. P implies Q. P implies Q is more or less like the English expression if and then, although sometimes we say implies as the English equivalent of it. So again, let's construct our truth table. We have two values. We have two distinct variables, so we need 4 rows. True, false, alternating factor doubles, true, true, false, false. Now we're ready to start thinking about truth values. Now to illustrate this, let's use an example and analyze how this works. Suppose I said to you, if I have time after class, then I'll bake cookies. All right. Now, the question to ask yourself to get an intuitive grasp of how material implication works, the question to ask yourself is, when would I be lying to you? Okay? So let's consider the possibilities. Suppose I did have time after class and I did bake the cookies. Am I lying to you when I say, if I have time after class, I'll bake the cookies? No, I'm telling you the truth. If I have time after class, then I'll bake the cookies is true, like the whole proposition is true, because in this particular case, I had the time and I baked the cookies. All right? Now, again, the question is, when am I lying to you? Let's consider the possibility when both of these are false. If both of these two are false, in other words, I have time after class is false, and I bake the cookies is false, am I lying to you if I say, if I have time after class, I'll bake the cookies? No, in that case, I'm telling you the truth because the whole proposition says, if I have time, then I'll bake the cookies. It just turned out that I didn't have time and I didn't bake the cookies. So this possibility is true, and this possibility is true for the whole expression. So our challenge comes in how to interpret the situation for these other rows. The row where having time after class is false, but I baked the cookies anyway, and having time after class is true, but I didn't bake the cookies. So let's look at the easy one, the third row. Suppose I say to you, I'm making you a promise, if I have time after class, then I will bake the cookies. Now, I've made you that promise, and here's what happened. I did have time, but I did not bake the cookies. What does that tell you about my promise? The promise was false. Okay? The promise was, if I have time, then I'll bake the cookies. I'm going to put a square around that because we want to highlight it. Okay? Now, consider this. Suppose I say to you, we're considering now the second row. Suppose I make you the promise, if I have time after class, then I'll bake the cookies. And let's say I didn't have time, but somehow I found a way to bake the cookies anyway. The question is, was I lying to you when I said, if I have time, I'll bake the cookies? No, I wasn't lying. What I was telling you when I made you that promise is only what would happen if I had the time. If I had the time, then I can't not bake the cookies. That's the promise, right? So this turns out to be true as well. And this basically is an intuitive way to approach what happens in the more formal and abstract truth table. For the first set of possibilities, if P and Q are both true, then P implies Q is true. For the second set of possibilities, if P is false and Q is true, then P implies Q is true. This is the possibility where that corresponds to the lie. If P is true and Q is false, then P implies Q is false. And if P is false and Q is false, then P implies Q is true. So these values correspond. This is an intuitive way to think about it. This is the definition of the operator material implication. Okay, now, suppose you say, well, what I really think is there should be a tighter connection because these two sets of possibilities, if there's a tighter connection, then the promise then these two possibilities would turn out to both be false. And that, in a sense, is the situation that we get with the biconditional or material equivalence, as it's sometimes called. Okay, so let's look at the truth table first, and then we'll explain what it corresponds to in English. All right, so we have two input variables, P and Q. So that's 2 squared. That gives us 4 rows. True, false, true, false. Double the alternating factor. False, false. Now we're ready to start calculating. If P and Q are both true, then this turns out to be true. If P and Q are both false, this turns out to be true. Otherwise, it's false. So now let's analyze what this means. In English, we often say if and only if. Actually, in colloquial English, we sometimes say, if I have time after class, then I'll bake the cookies. I should have put a then in there. Then I'll bake the cookies, but not otherwise. I've heard people say, but not otherwise, as a way of strengthening the connection between the two conditions, having time after class and getting the cookies baked. But the basic idea here is if and only if. So I will bake, if I have time after class, and only if I have time after class, I will bake the cookies. Now, if you think about it as if and only if, then it makes more sense to say it the other way around, because normally that's the way English would flow, is I'll bake the cookies if and only if I have time after class. If you think about it like that, there's not a problem at all, because with the biconditional, it does reverse like that. Like these two are logically equivalent, and we can easily prove that with a truth table. It's not the case, though, that P implies Q is logically equivalent to Q implies P. And the reason is because if you look at this truth table, we have an asymmetry here. The asymmetry is that the second and third rows don't reverse in the same way, because one of them turns out true and the other one turns out false. All right, so going back to the biconditional, these two are not logically equivalent, these two. So going back to the biconditional, the way we can think about material equivalence or biconditional is that P and Q have the same truth value when the overall expression is true. Otherwise, they have different truth values. I want to caution you, even though it's named material equivalence, it's not like the mathematical equals. It doesn't mean that P and Q equal each other. What it means, it's an operator. In other words, it takes inputs and gives us outputs depending on what those inputs are. Now, that's all our operators, and for each operator, we've constructed a truth table that constitutes a definition for how that operator behaves in every case, depending upon what its input values are.